with the animation, is it?
Morning all, we're just letting everyone in and we'll be starting shortly. Okay, we're a few minutes past now, so Thomas, if you want to start with the slides.
Are we not starting with the animation, Chris?
Yeah.
Human money. Join us now. Take a giant leap together.
Thomas, I think we're not getting all of that through, so I'll start and then let's get back to the animation in a moment. Good morning, everybody. My name is David Richardson. I'm Head of Innovation for the Strategic Innovation Fund at Innovate UK. I'd like to thank you all for joining us for what promises to be a really insightful set of show and tells covering the SIF Discovery, Data and Digitalization Challenge projects. Firstly, I'd like to extend a huge thanks to all the participating energy networks, especially the innovation teams, but also the project partners who've worked extremely hard over the last few months putting together and delivering all of these projects. We appreciate the way that you've embraced this new mechanism head on and will continue to work with the energy networks and all our wider stakeholders to refine the SIF process to achieve maximum impact. The SIF has two simple objectives. We're looking to deliver net zero at lowest cost to consumers and to turn the UK into the Silicon Valley of energy. The energy sector is obviously under immense pressure currently, and no one is feeling the pressure more than consumers. For us, this underlines the importance of innovation, and we believe that innovation can play a central role in making the UK the best place in the world to be an energy consumer and the best place in the world to be an energy entrepreneur in future. There are three pillars to the SIF. The first is strategic alignments with other funders and other sectors. The second, delivering fully in agile, which constitutes the challenges, the discovery alpha beta mechanism, and the way that the SIF team operates as a unit. Third pillar is commercialization and ensuring that we drive innovation to become business as usual as quickly as possible. Development of new products, processes and services that benefit people and drive down emissions is the central mission of the SIF. No single organisation can achieve all of these outcomes alone, and we've termed the process a giant leap together. Networks, regulators, infrastructure owners and governments will all need to work together on key problems to achieve these successes. Giant Leap Together has 4 periods across the year where together we focus on different aspects of innovation development. These are challenge setting, and you'll recently have seen that we've released our round 2 challenges, which will launch in September. Targeted ideation, where we work with industry and the networks to develop great ideas. Incubation, where networks can build their award-winning consortia. And acceleration, where the challenge is open and will join the ENA, Ofgem, BEIS and others in hosting the first ever UK Energy Innovation Summit on 28th and 29th of September in Glasgow this year. The round 1 discovery projects you're going to hear from are now in acceleration. The teams have been working flat out to put the pedal down on innovation development. It's been an intense start to the SIF programme. We need to focus as much time as possible on developing ideas, taking risks, and ultimately delivering value to consumers within the SIF. The aim of this first phase has been to learn fast, pivot quickly, and fail small. Some of these projects may have disproven their original hypothesis or discovered unknown barriers during their discovery phase. These are valuable findings too. It's better to learn these things early, take a different route, or return to the base camp and replan whilst it's still possible. Embracing positive failure is an important part of the SIF. Finally, I just want to thank all the Innovate UK team as well. Kate Jones and Manu Ravishankar in the innovation team, Chris Kunick, Thomas McGoy, Tom Paul and Amy Oswin on the PMO, and of course, Matt Hastings, who many of you will know as the Challenge Director. Also, a big thanks to our monitoring officers and expert panels. They've all worked incredibly hard to support the discovery phase, and without them and without our network colleagues, there would be no SIF. So with that, we'll move on to the Data and Digitalisation Challenge. Thomas, do you want to try the animation once more before we do that?
Yeah, I'll stop presenting this and then share them in the normal way. So hopefully that'll. Can you see this now?
I can. We don't have a sound though, Thomas.
You need to show your sound, Thomas. I did get the sound the first time and the animation the first time, David, so it may have just been a sticky internet issue.
Okay, no problem.
We'll move on to the data and digitalisation slide. Thank you.
So briefly, just to go over the Data and Digitalisation Challenge. The aims of the competition were broadly to decarbonise gas and electric energy distribution and transmission networks to benefit the consumer using data and digital approaches. We're looking at delivering the enabling digital technologies required to accelerate progress in all the other challenge areas. Also looking at improving data monitoring, availability, quality, collection, interoperability, access, and really starting to develop insights to third parties in order to increase consumer choices and improve efficiency, security, and resilience of our energy networks. There are a few things that the projects were asked to address, which include users and their context, constraints affecting the problem they've identified, opportunities for improvement, and environmental impacts. In particular, we were looking at some solutions which would help enhance more transparent and effective pricing and allocation of reinforcement costs in relation to new connections. We asked projects specifically to work in the open and utilize open source approaches wherever appropriate, to publish searchable metadata and data sets that were produced through the project, improve enterprise and business processes, and enable consumers to use their data in a way which helps them to engage in energy system innovation whilst maintaining privacy and security issues. Other areas of interest included how interconnected assets can help network customers and consumers interact and support the energy networks as we move towards greater decarbonisation, and how we could improve the visibility of infrastructure or assets. For instance, new digital backbones or novel uses of sensor or communication technologies. Interoperability has been a really important part of this challenge, and the interoperability of software platforms and data, both across the network types, but also other infrastructure sectors, has been really important. Using data and digital platforms in novel ways to improve network planning, modelling, and forecasting capabilities have all been part of some of these projects. So with no further ado, we can now move on to the next set of challenges. The first project that we have up today is the Virtual Energy System project from National Grid ESO.
Next slide, please.
Jonathan, Beatrice, Andy, could I hand over to you?
Good morning. Can you hear me?
Yeah, loud and clear.
So, good morning. I'm Jonathan Barker from National Grid Electricity System Operator. And we're here for the Virtual Energy System programme this morning. I'm joined from our delivery partners, Arup, IB, and Andy, who will come on later. If you can move to the next slide, please. You can see on the slide at the moment the partners in our project on the right-hand side, and we're supported by the networks towards the bottom. And we can move to the next slide, please. So the way we generate, manage, and consume energy is already changing for the better. Interactions between electricity and gas are increasing, and this includes the electrification of heat, transport, and developments in hydrogen systems. The energy system is becoming more variable and dynamic, and these changes are essential for achieving net zero and for a cost-effective energy landscape. And they also bring massive challenges and complexity, which necessitate changes in the way we operate. Our Bridging the Gap report in 2021 concluded that increased data availability and digitalisation of systems is fundamental to enable markets and technology to manage peaks and troughs. If you can move to the next slide, please. So the virtual energy system will develop an ecosystem of digital twins representing the whole GB energy system. Each digital twin will be a model of physical assets or systems which are linked to the real world through observations and data. The results of these models can then be used to change the configuration of those assets or to model future scenarios. To maximise their value, these digital twins, models and data must be developed and exchanged to a common methodology, the common framework. This is what this project is focused on. Each entity, for example, a generator, transmission, distribution network, would develop their own digital twin and share their data. These models and data would be shared in the virtual energy system. The data and models from these twins would be brought together to solve wider system challenges, for example, energy optimization, carbon reporting, or investment planning. And each use case will expand the value delivered by the virtual energy system. With our stakeholders and working with partners, we'll bring forward use cases which will expand the system represented over time. But in discovery, I'll pass you to Andy and B on the next slide, please.
Hi, good morning. My name's Andy Cavell. I'm an associate within Arab's digital team, a specialist in information management, and I'll introduce my colleague B.
Hello, everyone. Nice to meet you. I'm Beatrice, lead business analyst on this project.
Okay, next slide, please. So in advance of this discovery phase, we'd actually done quite a bit of work looking at the common framework for the virtual energy system. And as part of that work, we had identified 14 different socio-technical principles that would be required in order to better share information and to achieve the aims that Jonathan's already set out. These cover areas, so it's not just about the technology, we also cover areas such as people, process, of course, the data, and the technology that underpins that. And of those 14, we discovered that around 6 of them were absolute priorities that needed to be put in place first, such as raising awareness, engaging people, obviously governance, and the visibility of the data, improving that. So we felt that early on that we needed to actually demonstrate this common framework. Next slide, please. So leading based on the examples from, for example, Credo and the open banking sector, we decided that creating a demonstrator was going to be the best way of actually showing how to do this. So we want to obviously avoid any duplication of effort. We wanted to align with the National Digital Twin Programme and really demonstrate the value of having this common framework in place to ensure that different parts of the energy sector could really share their data. But we needed a use case. We realized we couldn't do everything. And so the discovery phase really tried to focus in on what would be the most appropriate use case. And through 16 interviews that we conducted, we were looking for a use case that would, of course, test those factors that I described previously. It would really engage the various stakeholders from across the energy sector to make sure that everyone had their say. It had to obviously appeal to a wider audience to have a use case that people could really relate to. And it also was important that we leveraged on the huge amount of existing work that's already there, whether that be platforms, technology, data standards and the like. And of course, it had to be theoretically feasible within the timeframes that the SIF funding was available for. It couldn't be something that wasn't able to be completed. So I'll pass over to my colleague B.
Thank you, Andy. Yeah, so this is the timeline of our 8 weeks discovery. And what I want to bring your attention to is actually how most of our time and focus was spent around sort of trying to identify the problem space with its users and the needs of those users that would allow sort of to involve actors across the energy industry and would provide us with sort of an effective use case to sort of demonstrate the common framework. If you can go to the next slide, please. Yeah, so we started with an initial engagement and very quickly we saw sort of a hypothesis really emerging from our conversation, which then we decided to carry through the discovery and test. And the hypothesis we sort of ran into was that the actual lack of end-to-end visibility and actually access to data that related to sort of asset generated energy, maybe the available connection on the grid and the network capacity and constraints, specifically across the transmission and distribution network, were actually sort of an obstacle problem, maybe to really accurately model, assess and even control the whole system flexibility. Next slide, please. So the theme of flexibility was something that resonated across all the actors across the industry we spoke about, albeit there was a slightly different definition of what flexibility meant. And so what we decided to do is to sort of provide some clarity for the scope of our discovery, and we refer to the Bridging the Gap net zero report. And therefore, for the scope of our discovery, we define flexibility as the ability to adjust energy supply and demand to keep them sort of balanced. Next slide, please. What we This is, however, is quite a big topic, and I'm sure people are more expert than me know that really well and are aware. So through our interviews and user research, what we found out that actually for the purpose of demonstrating the common framework, actually we should probably focus more on the supply side of flexibility, which really means trying to look at what can be done on the network to support the flexible use of renewable assets. And this means looking at how do we use our energy storage assets, connection, interconnection, how do we balance local supply and demand, this through the sort of visibility and access to the right data at the right time and level of granularity. Next slide, please. The other core thing is, once we could sort of had that more or less defined, was really to try to understand what is the value that this can brings to core users, and how does this meet some of their needs. And so you see here we've identified 4 macro category of users, and they sort of start to create the sort of thin slice or vertical slice of actors across the energy sector. And I will pass it on to Andy, if we can move to the next slide, who's going to sort of talk us through what then this demonstrator will look like.
Thanks, B. We created this diagram to try and explain how the demonstrator would potentially work. Having followed the various discussions that we had with our partners and across the networks and with the ESO as well, it was very clear that there's obviously a lot of data out there, but as B explained, not always in the right formats, frequency, or availability to each different actor. But there was definitely a requirement and a need to share this information. So the very first thing that we propose the demonstrator to do is really assess that data need, what data is available, its formats, how granular it is, and then make that available and discuss that amongst it, so each group could decide what was required. So whether it be data or policies or information, data standards, the first place of the demonstrator would be to show that all together. And that also includes the gas network data as well. The very first activity would be to determine the relationships between the data. And because some of the assets are of course common across the network, and we need to really understand how they related to each other. So a knowledge graph would be the way of defining that. We'd also look at the data standards. Obviously, having a data standard is key, making sure that data becomes interoperable and it's well documented as well. So during the data standards, we look at how the data was formed. We look at existing standards such as the SIM, which is the Common Information Model that's already underway and in use, but also metadata standards as well are key and important. But of course, one of the most important ways of sharing data has to be the data licensing. It was very clear from our discovery phase that this could be one of the biggest barriers to sharing data amongst other actors outside of organizations. So it's very important that we started this conversation early as part of this discovery and as part of the demonstrator to really determine how do we unlock some of this data in a controlled and secure way. So to make sure that we had the right agreements in place and maybe a licensing template could be formed. And of course, once that's all been agreed, the next thing is to share the data to make sure it's available, it's open, but to the appropriate people. And there's already significant effort in this area led by Icebreaker One with the Open Energy Platform. And so there'll be an evaluation of that platform and start to agree how data could be published and shared and who would have ownership. Now, all the way through, these social technical factors at the bottom there would be tested. And as part of our report, we outlined which of the different socio-technical factors form each one of those various component parts and which would contribute to it. So throughout the demonstrator process, we would be proving that these factors were required to make for better sharing of information, and then ultimately to have the data available so that the improved modelling and analysis could be formed by each of the various parts of the energy sector to model for system flexibility and the visualization of that data. We very much make sure that we were aligned and linked into existing work and existing other things such as the National Energy System Map. BEIS have their own energy system digital twin demonstrator, but that's at the domestic flexibility layer. So there's obviously a very key area that we share information between those two. So I won't go into too much more detail, but basically this was what we came up from the discovery phase and how we would progress things forward towards net zero. So I'll move on to the next slide. I pass back to Jonathan.
Thank you. So taking this forward into where we're going next, this week, National Grid ESO and our project partners, we've submitted an application to continue into alpha. We plan to use that 6 months to start to assess some of those risks and the mitigations identified by Andy on the previous slide. The SIF Alpha project will continue to focus on the development of the common framework, the underlying section of our work streams. And this is going to underpin the whole energy digital twin ecosystem. We'll start by examining those assets and the data. We'll move through into the data relationships between systems and parties, and we'll use that to identify what standards need to be implemented. A big challenge is the data licensing that was identified, so we'll be reaching out to understand how that works, both for regulated entities and for non-regulated parties in the system. All of this will be brought together into a cost-benefit analysis, so challenging some of the feedback that we've received during discovery, that it would be valuable to have a clearer understanding of the benefits and the costs in building out this ecosystem. So we made that a key component of Alpha. The project's going to be supported through stakeholder engagement and use cases as it has been in the past. We'll be working closely with network partners who have related SIF projects, and also through ESO's CrowdFlex project, which you can learn more about on Monday. For Alpha, we've also added SGN into our network partners, and we're also joined by SSEN Transmission. Long term, our ambition for Beta would be to start to develop these solutions that are needed to make the system a reality. Those could include central services, open source tools and standards that are necessary to exchange and combine digital twins. With the demonstrator, Alpha offers us a way to build these out and to scale it. So we can pass to the next slide, please. We'll just conclude and thank you for joining us this morning, and all the partners are on screen. Thank you.
Thank you very much from everyone at the Virtual Energy System project. We will be taking a couple more presentations before our Q&A session, both from Sven on projects entitled Entwine and DigiGift. If there are any questions that you have coming up through the presentations, then please pop them into the chat, and then we'll have a 15-minute Q&A session at the end of these 3 project presentations. There's no question too obvious or to go in the chat, so please do just throw questions in and let's get a bit of a discussion going around these projects. So if we could now move on to the next one, Thomas, which, as I mentioned, is Entwine, and this will be presented by Panos and Nico. Over to you.
Pano, are you on?
Yes, I'm here. Hello. Hi, everyone.
Go on camera. There you go. Good morning, all. I'm Nico Louvranos from Digital Catapult, and together with Dr. Panos Papadopoulos from the University of Strathclyde, we will walk you through Entwine, our SIF discovery project led by SP Energy Networks. Next slide, please. So Colin Gold and Michael Eves from SP Energy Networks will also support you in the presentation. And this project was done with the support also from National Grid ESO. Before we get started, Colin, Panos, and myself, as the leads of this project, would like to extend our gratitude to the people that made this project a reality. From Scottish Power Energy Networks, Michael Eves for his unending support from beginning to end, Jamie Monroe, Cameron Cox, Finlay Dowds, and James Yu. For National Grid ESO, the superb Jonathan Barcroft, who you just heard, for being a true partner on the project, and Carolina Tortora for her support behind the scenes. From Strathclyde, the tireless Bruce Stephen, Chitek Hong, Rory Telford, and Robert Hamilton. And from Digital Catapult, the inspiring Hema Ramamurthy, Darren Prehai, JC Kuye, and Rob Smith. And without further ado, let's get started. Next slide, please. So what problem did we aim to solve here? It was the need for a real-time simulation of the electricity system using a digital twin technology. With the anticipated electrification of heat and transport and the proliferation of DERs connected at distribution level, we see an increase in demand-side flexibility. And to maximize the benefits of this increased demand-side flexibility to the consumers, we require better visibility of the potential impact and efficacy of these assets and the impact they might have when balancing the national electricity transmission system. And therein, we found lies the opportunity to use a digital twin technology along with artificial intelligence to simulate, model more of the electricity network much closer to operational timescale in real time. We posited that this would allow us to make better decisions in operational timescales and help us effectively manage the increased complex interactions between distribution, transmission, and the ESO. Next slide, please. With this in mind, we focus our project in exploring the technical feasibility of a twin of the distribution system. We wanted to explore how digital twins can support visualizing, understanding, and evolving a system as complex as the UK's electricity networks to respond and adapt in real time, and also forecast future scenarios that will allow us to unlock the benefits of increased demand-side flexibility, as we discussed, and as per the problem statement, in essence. To this end, we aim to do the following. We wanted to establish the minimum viable product and the highest value use cases which we identified, determine the art of the possible based on the availability technology and the data at the time we baselined during the discovery, and then outline the architecture for an interoperable digital twin considering best practice and also the other projects as we saw from ESO. And finally, to develop a strategy to verify our twins functionality. Pano, over to you. Next slide, please.
Thank you, Nico. So, well, starting from the user needs, so throughout the discovery phase, we had a number of workshops with different teams from SPEN and the ESO as well, and focusing on understanding the user needs and user cases for a distribution network digital twin. So the idea is that the digital twin will offer greater near real-time visibility. That is, we are talking about operational timescales, which is a few minutes basically. We focus on near real-time visibility of resources connected to the distribution network, as well as at the same time identifying potential constraints so that we can make sure that this available flexibility can be actually delivered while maintaining the network within operating limits. And this can be useful for more secure and effective balancing actions and unlock this available flexibility eventually. So we have identified three main use cases that can span from 33 kV down to low voltage networks. First one is related to improving DER visibility with respect to active and reactive power at the interface points, as well as to investigate the possibility to disaggregate what is the mix of energy sources at this point. Expanding from the first one, the second case is related to identifying now constraints with respect again to active and reactive power. And this is related to the calculation of the so-called operating envelopes to actually now quantify how much active and reactive power we can get at particular points or interfaces of the network. And then both this and the first use case is of interest to be calculated for the current system state as well as for a few settlement periods ahead using, for example, short-term forecasts. And finally, we can also run what-if scenarios through the digital twin, for which I will be speaking a little bit more in the next slide, please. Right. So as described earlier, the main aim of the project is to develop a digital twin of a distribution network that is effectively an augmented distribution network model, if you will, or modeling process, which uses real-time measurements. And this is conceptually visualized in this top right figure. The focus of the functional architecture is to enable distribution network visibility of the current state, so near real time, to identify thermal and static voltage constraints, and also calculate the operational envelopes at different points of the network that can then be used by the ESO for secure and effective balancing of the system. So, for example, increased visibility can be useful to the ESO when flexibility services are activated from aggregated resources that can appear under different GSPs, as also visualized in the figure at the top right. And an example of such an operational envelope is shown also at the bottom right figure, where the possible operating region of active and reactive power is now visualized. This is a feasible, from a technical perspective, operating region at the network interface while respecting the network constraints. And consequently, this can be used to quantify the amount of flexibility that can be accessed from various points of the network, for example, under particular GSPs. And as visualized in the figure, also such envelopes can be calculated, for example, under each one of the GSPs. And using the information, the real-time digital twin model representing the current network state also allows for running what-if scenarios in operational timescale. So, for example, using short-term forecasts or testing the impact of different potential balancing or even other operational actions as well. We also explored the possibility of extracting information to disaggregate the generation mix that can be then used for advanced modeling at the transmission interface. So, for example, using this information to allow for use of more detailed models from the ESO, especially for dynamic studies as well. So, next slide, please. Thank you. And so we came up with a proposal of developing digital twin models for 33 kV voltage. We call this twin top, as well as down to low voltage, and we call this twin end, with more or less similar functionalities and capabilities for them, but just separated at different voltage levels due to the network size and expected also computational requirements to execute them. Some general considerations to build such models are related to assimilating existing SCADA streams, and we looked into different systems, sensors, availability of data, and so on that Nikos will be talking about later. Use of forecasts, obtaining the network topology from GIS, dealing with missing or unavailable data is also an important aspect, something that can be different for higher or lower voltage levels as well. And in this schematic on the right-hand side also shows the deployment of such models down to the low voltage network. I will now pass on to Nico as well to talk about the data architecture. You are muted, Nico.
Rookie mistake. Thank you, Pano, and the Strathlight team. The great work on the functional aspects of the project. And now I'll walk you through what we call the data and architecture workstream led by our experts in DC. With the support of different teams within Scottish Power Distribution and Transmission, and National Grid ESO, we embarked on several deep dive sessions to ascertain the extent to which data is available now through existing data feeds and future planned ones, and hope to identify gaps and methods to fill these in future phases. So from the ESO side, we discovered that grid balancing is only using a limited number of DERs at this stage, and also ESO has no visibility of what energy source is dispatched and from which GSP, whether the GSP is a DNO or an aggregator. And also ESO cannot really even request a dispatch at a certain GSP. So there's kind of that visibility element is very apparent from the ESO side, and we also heard that also from Jonathan earlier. So essentially, given that outage planning generally is done with conservative assumptions, just because it's best to be safe than sorry, as we know. From the DNO side, it became clear that the visibility and data available progressively diminishes as we move from the 33 kV down to LV, while the number of assets actually exponentially increases. That creates, we know that warning signs of an at-scale problem there. We also had extensive discussions around how laborious and manual processing is of any data that currently exists, and how hard it will be to actually make it for a use in a real-time basis. So, and essentially, these are the points. These all point to the opportunity that the digital twin, with a combo of AI and machine learning technologies, could potentially address performance, scale, and visibility. Next slide, please. And then we then proceeded also to baseline Scottish Power Energy Network's current and planned architecture that we could potentially leverage to develop our digital twin. So we were happy to see that, obviously we won't be starting from scratch. There's a lot of existing infrastructure and components that could be repurposed and focused on the specific use case. ED2 plan has digital twin enabling factors, but not for real time. It's more for long-term planning. So the minerals are there, but there are also tools that could be again leveraged if at scale with the right design impetus behind them. But also we discovered the usual barriers you have when there's a transformation program where you have the real-time systems quite tight and air-gapped for obvious reasons between the IT systems, and the challenge that these needs to be brought under a single framework and a single, let's say, enterprise bus, as it's called within the SP energy parlance, to be able to, in one place, address, collect, and analyze and model data, because this is the usual problem when you're trying to aggregate a lot of data and process it in a single time, align them so you can do everything in real time. And also we took a stab at a high level at this stage, because it was only a 2-month project, on what a Scottish Power Energy Networks needs to consider moving forward from a target topology to support the digital twin, given the exponential growth of data we expect to have to ingest and also be able to process it in real time. And Pano, over to you to look at the way forward from where we are.
Yes,
Next
thanks
slide.
again, Nico. Looking forward, we've identified that we are basically at a stage after the discovery that we can define in detail the specific network location to start building proof of concept applications, basically, and actually to proceed to develop a digital twin. Initially, we suggested using offline or synthetic data so that we can explore first the practical implementations and computational aspects, without in the first stage at least having to take into consideration all the live information flow between systems in one go, basically. So we suggested the twin top and twin end, as we call them, implementations to investigate particularities related to different voltage levels, as well as their associated computational needs, which we expect to be quite different due to the scale of the network. And at this stage also, it's worth mentioning that including a cost-benefit analysis to inform priorities related to voltage levels would also be useful. Define, for example, levels of available flexibility at different voltage levels and consequently prioritize accordingly the building of these digital twins. And I will pass again back to you, Nico, for the final slide.
Thanks, Panos. So as we discussed, given the sheer volume of expected data and that the digital twin we envision we need to process, looking forward, we would like to also explore the feasibility of using machine learning based modeling and the development to be able to do this at scale. Because we expect that, Panos suggested, we definitely need to run POCs with physics-based models just to see if the maths work, first of all. But we know that at scale, we will hit very quickly performance issues. And that's why we would like to explore kind of the ML, as we call it, the black box method, the data-driven method that we could employ to identify what performance gaps might exist and the requirements that should underpin such an endeavor. And at the same time, also, it's very pertinent to actually go to drill down to the further detail of the architecture and implementation requirements to make this a reality. Again, aligning with whatever Scottish Power Energy Networks they have in the ED2 plan and leveraging what's good and helping them redefine what needs to go, what we need to go going forward. And here I would like to end our presentation. And again, thanks to everyone. Thanks to also to Innovate UK, David and the team for being on our side from the beginning. Not an easy job. So thanks to everyone. This has been fantastic for all involved.
Thank you very much.
Thanks a lot, Nico. And it's been really encouraging to see some of the capability from other sectors come in through the digital catapult to the programme. Thank you.
Thanks.
So the next project that we're moving on to is another one from Scottish Power Energy Networks. This is entitled DigiGift. So I'll hand over to the team to present this one.
Oh, okay. This is how you, Alex, can you show you? Okay. So yeah, basically, I think we do this business case on behalf of Scottish Power Energy Network. So we have a couple of people doing this, and it's me, and also I miss this Andrew Andrew Chalking, and then we have a Dr. Anwar Marty Sensina, and then we have a Professor Zirong Hu. Okay, so we basically feel that we need to focus on more kind of digitalizing it's a kind of platform. All right, okay, next slide, please. So basically, I think I just tell a little bit story about where we are. So we actually being a little bit a long journey. Start with the digitization of substation. We build the virtual substation acceptance test platform, training platform. Basically, it's kind of virtual digital twin within the substation. And we also participated the Scottish Power Spain. The fitness is called Future Intelligent. It's the real implementation of digitization in their network as a substation. So it's a real digital substation. Then after that, then we feel that everything we did, there's a big problem is because the cybersecurity is one issue. If you have the share data or the share platform or the data available. So this is the issue. Then we start looking into cyber resilience and focus on the electric substation technology. So then we felt that because there's the issue, if we want to move forward in terms of digitalization, and we need to be clear. So we do digitalization, and then digital transformation. So majority of people start to looking application use case. So we already done that. Then we felt that it's an issue of that we needed to looking into interoperability because we need to have data across the party. So this is a part of digitalization. Then this involves big data. Then as well as big data, there's issue of data integrity and data quality and assurance. How you make sure that you get the data acquisition because of being sort of unreliable communication link or etc. Then obviously the network security is important, extremely important. So the challenge is that we need to look in the share data and process the infrastructure. So we don't need to duplicate like a bespoke. Every have a data acquisition have its own system. Then we also need to enable support the future, the real-time, the data-driven application. So many already in the previous presentation is about digital twin. So for example, there's a challenge if we do wide area monitoring, system integrity protection control. So we basically move from very fast localized protection into really to control generation, which is really need faster, not like unlike a traditional SCADA system, you can have a bit slower. And then we also look into market service or coordination across party. Okay, next slide, please. So this is our exactly summary. So the digital twin, we aim basically in the discovery, we try to build integrated and robust the cyber intrusion defense system into the shared data infrastructure in order to manage data integrity, quality, and security, and the data privacy for the business as usual, as well as to support the future real-time data-driven application. Just to say digital twin. So in discovery phase, we look into several issues. So we define issue and also we look at the challenge that we identify. To support our proposal solution, we need to have what is the innovation, what is the business case. So we did a cost benefits analysis for 3 key challenge area, and they are the shared data infrastructure for better data collection and integrity according to analysis. Then we also have a business case for integrated intrusion defense system. Then we quantify the value of flexible service coordination in using as a use case is the Scottish Power distribution area. So we finally draw conclusion. Next slide, please. So the problem is complexity of the scale achieving net zero will require more agile, flexible, a secure interconnected network. The energy system transition and it's the digitalization will play a vital part to facilitate net zero economy and safeguard the UK global leadership. Based on literature, the identified key area are so lack of the data set interface among different the asset common business. So we need the common or standardized the framework, and the lack of the shared infrastructure and a confident data integrity and quality due to unreliable basic say communication and link, or especially IoT. If you want to move that IoT technology, then remote data collection from SCADA and IoT sensor will require a proper security solution that can be guaranteed the integrity of each separate security zone. The lack of the cyber intrusion defense mechanism, then more advanced, basically to against the more advanced, such as the malicious false tripping attack, which is really bad to the power system SCADA and our processing system in order to basically this attack in order to disrupt the power system. Okay, next slide, please. So we did a for business case. Just this is example. We say we have a share the data infrastructure. So for example, in the left side, figure 1 is a bespoke, or we call dedicated. So in this case, we have a SCADA system, has its own data, its own infrastructure. Then we have, let's say in Scottish Power, we have a visor, basically frequency project. Then we also looking into wider area protection and control. So this all have its own, let's say data, and there's no standardized between them. And then we have, let's say they all collect the sensor or CTVT, all unified, because we don't need additional probably data because we have already enough sensor in the system, in the power system. So in the future, if you want to add an application, additional application, you need to add a slightly different sensor, or maybe using the sensor which translate a different data format and then to have application. So that's the left side. The right side, we propose that we should have share the data. So we do exactly the same base case. Then through this shared data infrastructure, then in the future, if we adding additional application, then we don't need to change our database. So assume that sensor or the network sensor already installed everywhere in place. Okay, next slide, please. So this is the business case. Basically, we study to based on the data cleaning technology. So assume that if the moment all this the dedicated system has its own database. So if we can have a share, then what we can achieve, assume we have, let's say, using 3 database with 30% overlap scenario, then we can save roughly 2070K. And if we move to 50% overlap scenario, then we can save quite a bit. But then if you have a 6 database, maybe 6 application, then we can save a lot more. Now, in the future, if you add a little more, then we can do that. Then also another aspect in the left side is called data maintenance. So if at the moment the data maintenance is very much a dedicated individual. So you have this system update, and then it's separately. So that maintenance the cost for maintain 6 database. Then you can have a saving for 80K and 200K per annually. So that's what we base our assumption. The next slide, please. So then we have a business case for looking into cyber risk, and then with and without investment. So in the left side, the figure 5 really looking the risk assessment, and we're using either events tree, which is based on National Grid the data, the publication, that we use the same figures, And with our Markov model decision process, which is you can do this more dynamically. So when you have an attack, you can changing more and more kind of dynamic. So that's why we have a verify. So the left side is this red, basically say if you have the without investment, then the risk score from risk assessment will be from 6 to 8, and it depends on the year, because today year is 2002, which is a 6 score, but then because of this, the more digital, more the cybersecurity threat, then 2031 there will be score 8, which is quite dramatic. Then the blue, which if we implement a cyber defense system or cyber security, then they will be reduce the risk dramatically. So the left right side of this, we just try to put into the cost of benefits related to if you have a substation outage. Then today, 2002, then we have a roughly 70K per transmission substation. Okay, then we were looking into the 2013, then there will be easy reach is about 1.2 billion substation. So basically, each substation being cyber threat, then will be costed that much to maintain. Okay, then you have a scale up, which is quite significant. Right. Okay. So next slide, I probably hand over to my colleague Alex, then he can talk through the rest of the slides.
Thank you very much, Hayu. So my name is Alejandro Martinez, Alex for short. This is the work done by myself and my colleague Andrei Cherkin. So one of the key aspects of this platform is the ability to share data at different network levels. So this has an implication on the type of services that we can provide to the network, to the customers. So just to illustrate this, we can begin with something that pretty much already exists. So what we have on screen are different services that the University of Manchester has been involved in the last few years, such as Class and Smart Street. These ones were led by Electricity Northwest. So these services, which are focusing on minimizing the voltages, you can see the voltage in the figure here, they traditionally work independently. They were created with their own bespoke infrastructure, and now there is a lot of focus on trying to bring them together so that they can maximize their productivity. How is this similar to what we're doing here? It's as we're creating the platform, the idea is that rather than going through that transition of going through the project, then going through another project to put them together, we want to have this platform to enable us to have them from the beginning integrated in a similar fashion, in a single platform, so that we can have this coordination of services. So in this example, if you can go to the next slide, which is the animation, you can see that just by having this exchange of information between these existing services, something that it's already there, you can maximize the ability of those services to, in this case, reduce the voltages. Some of these services, in this case, one of the Smart Streets in Bus 5 is doing a reverse to what it would normally do under normal conditions. But those are things that traditionally you don't get to see at the different levels. This would be what would be called conflicts. That is, from the perspective of one service, something that might be or appear beneficial might not be beneficial for the system. So there is expense of services at a different level to try to compensate. So basically you're spending capacity just fixing these conflicts. So that means that if you're able to have that coordination, if you're able to not only fix those conflicts, but profit from the synergies, you can release capacity of already existing technologies. So if we go to the next slide, and here we're going to be using a concept that was also mentioned by Panos in the previous presentation, although we call it PQ maps instead of envelopes. What you can get once you have this coordination is you can effectively increase the capacity of your flexible resources. So just by having this platform where you can have this trade of information, this high level coordination, you effectively increase the the volume of flexible resources that you have there. So what is the value of that? What would be the value for Scottish Power? What would be the value for the UK? And well, the way we calculated it is we use the future energy scenarios to determine across example networks what would be the integrated flexible resources throughout the future energy scenarios, and what would be the value of having them operating independently, bespoke, versus bringing them together in coordination. And that is the difference that you would see on the left. So we do recognize that those flexible technologies, those services already have a value, and what we're mapping is the incremental, the difference between having them operating independently and allowing us to do that coordination. Now that we have that extra capacity, we can map the value of that capacity to the type of services that we can get. Obviously, there's a lot of uncertainty it's surrounded here, so we created a wide range of considerations, not only on the future energy scenarios, so there can be a high, a rapid, or a slow integration of resources, but also on the value of the services. And that's why you see different curves of values. And based on that, we took a central view, which is a bit conservative, but this means that we are quite comfortable that this type of services can bring about 31 million at the Scottish level by 2050, which translates into more or less 300 million at the UK level. And so this would be the third business case for this service. If we go to the next and final, to the next slide, this is just basically a summary of what this platform is meant to do. So one of the key aspects is we want to have this platform to share the information. We want to basically avoid having to create new infrastructure every time we want to have a new service, because that's more expensive, that is slow. Then for this to work, the platform has to have capabilities for data processing. It's not enough to just have the data. We need to be able to use it to effectively do something with it. But for that to happen, we're going to the third bullet point. This platform, and this is one of the main contributions of the work, has to be developed with the aim of being cyber secure. And this is not only making sure that the right people can access the information and manipulate it, but also that if someone is able to access the data and starts manipulating the data, that there are algorithms to identify if that is malicious. So it's not only not letting people in, it's also checking their behavior within the platform, which is a key difference with other views of cybersecurity. And finally, again, something that was also highlighted in the previous presentations, we were focused on digital twins. The information, the data stream has to be close to real time, because those are the requirements that we can see from the other projects. So there has to be this alignment between what the platform is doing and what is happening right now in terms of research. What are the requirements for development in the UK? And if we go into the last, now the final slide, we're going in the other direction. It's just the Q&A. So thank you for your attention, and I think we can proceed. Thank you very much.
Thank you. Yeah.
Thanks a lot, Alex. If I could invite everyone who's just presented in the last three presentations to come back in. And if we just drop the slides for a moment, Thomas, so that everyone can be seen. We've got a small number of questions that have come through, but a lot less than in our sessions yesterday. So if any of the audience have something on their mind, please do drop them in the chat and I'll share them with the projects now. But starting with the virtual energy system project, there's a question around whether you've looked at the work undertaken by the National Underground Asset Registration Project, NUR project, and will the common data approach that you're using interface and be interoperable? Who'd like to say that?
Yeah, I can take that. Yep, we're certainly very interested and have already sort of reached out to the National Underground Asset Register. I think the key areas that there's a good overlap there is, of course, in the data standards, because when the information has come together for all the buried services, and apparently is also including some overground services too, there needs to be a consistent high-level data model. So that's obviously going to be very useful as part of the data standardization piece for the common framework. Yeah, and it goes more to just the energy system assets as well. So certainly one area, and also the metadata that they are going to be proposing to use. So there's two key areas that can definitely be useful there. That also, and the mapping the geospatial element to this of NUR, because obviously that's a key area. So definitely I think there's a lot of synergy there. With regard to the other question around the live data streams, I think that's all for the assessment. I think that the last presentation there, we heard that there's a great need for real-time data, but it's a case of listening to what is required, documenting that, and then enabling that to happen in future through the common framework is what we're about. We're not trying to dictate what data should be there. It's about listening to the use case will dictate that.
Great, excellent, Andy. Moving on to Entwine.
Yeah, I can answer that one. So what factors will inform which locations to use as a POC and how you will make the assessment? So the main thing for us, because we had a lot of discussions with the teams internally, there are some projects where there's going to be more LV, let's say, monitoring happening. So we will try to identify an area where we have as much as we can get at the moment, just to get a bit richer data, and potentially use one to compare that has very little and see at which point it becomes very hard to actually extrapolate, because this is the ask, like how low, as we call it the limbo within our team, the limbo test, how low do you need to go to make it work? Because there's going to be a point where it's just not enough data to extrapolate, and that will dictate potentially new LV monitoring plans down the line. So we will use it, it's like twofold, use it for the project, but also inform where else do you need to be going. That's in a nutshell. Pano, if you have something else to add on it. And the assessment, yeah, I mean, maybe you want to add something on the assessment, Pano.
Yes, thank you, Nico. So yeah, I mean, as a general note, I would say in general locations with high level of distributed resources or other technologies that can offer flexibility from the technical perspective would also be of interest to target it. I think the flexible networks trial areas from SPEN, from past projects could be a good starting point from that. And we also kind of identified one case where that might be of interest, where this flexibility might shift between different GSPs. So these aspects also will be of interest from the technical perspective, I think.
Well, if we have a physical event in future, Nico, I'll be looking forward to seeing a live demonstration of the limbo test.
I'm very bendy. Yeah, I can do that. No problem.
Right, we've got a comment from Simon Hart, who's in Innovate UK as well. He runs a lot of the digital twin programs across all sectors, just encouraging all the projects to join the Digital Twin Hub. And UKI and BAYS will be using the Digital Twin Hub to engage with companies on digital twinning. So I think that's just a call for action there. I've got a couple of questions myself. One of them is whether there are any regulatory issues that you've identified for your project so far. Is there anything that, from a regulatory or consumer protection perspective, might act as a barrier to the implementation of digital twins? And that's for all projects, really. So who would like to take that?
So shall I come from Reg Energy System side? We've had a look through the last few months at how do we maximize engagement? So the Virtual Energy System will be a whole system. There are regulated networks where codes and license conditions drive what data should be shared, what formats and what timescales. But wider in the whole system, we've got to link into things like charging specifications, for example, whether we can get access to data from other sectors. And these things are stretched beyond regulation just in energy. So we are looking at some of that broader challenge of how do we build this in a both a regulatory suitable model, but also a commercial model that can open up access to some of that extra data and extra information.
And from a privacy perspective, there's obviously a very strong focus on consumer rights to their data through the smart metering program. If you start looking at being able to identify granularity on the system from a network sensing perspective, does that raise new issues with consumer privacy, or do you think that can be protected in the same way?
Go for it.
So that would all have to be addressed, we have some example of how other country or energy system like the Estonian one have addressed that, but also initiative in the UK they've sort of addressed it like open banking and what they've done there. But definitely there is an issue around sort of understanding the sensitivity of your data, and as you said, the legislation that are attached to that. There is GDPR and other things that we need to sort of account for. The concept of consent. So we are not there yet, I think, but these are definitely core key topics that we need to be addressed, because we need to get to be able to access and use the right information at the right time. And so it's going to be key to enable that. And we need to sort of work out the answer to those questions.
Beatrice, you mentioned Estonia. Have yourselves or any of the projects as well looked at developments in other countries, and how do we compare in UK places?
Yeah, so as part of the virtual energy system work, we did a precursor study, which was a sort of benchmarking report, which I believe is published on National Grid ESO side. And what we were looking at was effectively an example of other connected digital twin ecosystem across the world, which spoiler, there are not really none at this point, but there are people that are making sort of progresses in towards the space, and some countries that are working out to around the question around sort of use of customer data, one being Estonia and Australia. So I will pop the link in the chat, and maybe that is something helpful for others, and you can reach out for contacts to us, and we will happily share more.
Brilliant, thank you. And just as another thing to note, on the 24th, so next Tuesday, I think, the Connected Place is Catapult hosting a digital twin event. So Simon, if you're able to pop the link to that in the chat, but I think that's quite a good way of getting an overview of the developments that happen in other sectors as well. We've just had another question come in, which is, how are you going to have best cybersecurity when it has been demonstrated by anonymous hacks?
Okay, I think this is for me. Basically, I think we have our virtual substation in the lab already. So we've been testing various cybersecurity IDS system, various commercial product already. And then we also have our real substation. Obviously, when you're doing demonstration, it's very dangerous if you go to a real substation. So we can actually demonstrate in our lab, and then to basically to have a, let's say, enormous hacking, then we can monitoring, then we can do our different systems. So that's what we can do.
Do you do an assessment of the tools and systems that you use?
Yeah.
Is there any way of assessing the vulnerability of different ones?
Absolutely, yeah. We've done that already, but now the only things for this one, we want to move to the network, in our learning experience, move the network rather than just focus on substation. So that's what we try to model, and using ITDS to build some real system, and then we can have actually real devices to test it in our lab. So that is what we can do.
Great, thank you for that. The final question, unless any of us come in, is I was just wondering to what extent, to get visibility of the smallest distributed energy resources, do you feel you need to work with other parts of the sector, like suppliers or EV charge points operators? Is that requisite to all of this, or is it something that can be done purely from the network side?
From our side, we look towards aggregators as well, potential aggregators as partners, because they also become, they also present themselves as a GSP, which is relevant for ESO as well. But also, if they're not, they would be wish you to see how can they use that data also to inform their bidding decisions. Before they even bid something in that is hidden behind a constraint, maybe they can already preempt what is available, given that they also have the information. So it becomes a tool for all participants on that kind of flexibility, let's say, market. I mean, that's the hope and dream, right? Pano, I don't know if you have anything else to add on this.
Yeah, no, I think that covers the key points. So I think that aggregators might be, it might be useful to include them at least in discussions related to this definition of the available flexibility under this GSP, for example. So.
It is also a space that we would like to be expanding towards in the virtual energy system, whether it's a day one activity or whether this is something that builds out of the demonstrator. We've from previous NIA projects, for example, the Sheffield Solar project, the ESO was working with University of Sheffield on, looked at how you can aggregate up distributed inverter data to be able to estimate solar outturn within a given region. So we do have experience of how do we gather up information from all these different parties. The virtual energy system would stitch that together in a way that it can be reused for other use cases. It's something we need to evaluate over time.
Great, thank you. Provide some clarity, and if there are any of those groups that might be interested in engaging with the projects in future phases, do get in touch. So with that, we'll have a break now for 10 minutes before coming round to the next group of projects. But thank you all for presenting and asking questions, and we look forward to seeing how things progress in the future.
Great, thank you very much. Nice to meet you.
Thank you, everyone.
Okay, bye.
Thank you, everyone.